All right. Welcome back, everyone. That was a weird Thursday. um, I really don't know why we cancel classes so early in this day and age, but I don't want to waste a lot of time talking about that silliness. Unfortunately, we did have to cancel class even for an online class, so that's going to make it even more challenging to get through all the material for the semester. Basically, I think we're just going to having to cut a section or two. That's usually what happens, and I can't really make any exceptions. A part of me really wanted to just throw up the video that I had already recorded that you're going to be seeing today, and just saying, hey, y'all can watch this, but I didn't want to try and break any rules as much as I felt like that should still be everybody's responsibility. So we're just going to pick up where we left off. We're going to start 1.5 in just a few seconds. Just reminding you of a couple due dates. 1.3 and 1.4 are due today. And then 1.5 is going to be due a week from next class. So this date actually reflects something previous. It's going to become the 11th. So 1.5 is going to end up being due on the 11th because we will not finish that material today. But again, don't want to waste a lot of time. So let's go ahead and get into it. As usual, I'll be in the chat in just a couple minutes if you have any questions.
All right, so 1.5, quadratic equations. We're going to study these from a few different angles. We're going to solve them in a few different ways, more specifically. And the first thing that we're going to approach that with, the first technique, is going to be factoring. Now, the top of the notes for this, I just have see factoring document. Now, I'm not saying that you're going to look at it outside of class. I am going to actually review this. I said that I would eventually. This is not going to be a super in-depth review. I was looking at it earlier, make sure I had everything in place. But this is all of the different types of factoring that I don't want to say that you can use, but that would get the job done. So if you have ways of completing a problem where it requires factoring and you didn't do it via a way I say, guess what? That's completely fine. There are lots of different factoring methods. I have never learned all of them because there's literally hundreds. I have actually once or twice in my life had a student introduce a method to me that I had not seen before, and I might like it. It might have its quirks, problems, successes, all sorts of things. So you go with what you're comfortable with. But the point is, you are pre-calculus students who have been taught factoring previously. At least you should have. Otherwise, you probably shouldn't be pre-calculus students. And you are supposed to have retained that knowledge. Now, we understand that retaining math means you probably didn't use it for a few months and you've half forgotten it already. So that's why we give you these quick little brush ups, touch ups. I don't know what I was trying to say there, but I like to give quick reviews, or at least give you access to documents and web pages and things like that, and extra homework assignments that you can take the time on your own. So let's get into it. The first major factoring kind of tactic is using a formula. And we're generally trying to use formulas for binomials. What's a binomial? Well, it has that prefix or prefix of bi, which means two. So binomials are polynomials with two terms. Something like you can see an example, x cubed plus 64 right here. So that has two terms because it's this thing and this thing separated by pluses or minuses. So you have three very common formulas. You'll notice that there's four things up here, but I said three common formulas. That's because the second one is not really a formula. The difference of squares. If you don't have this memorized yesterday, that's a problem. And I'm exaggerating with the yesterday. You know, I'm a little silly. But you need to have this one memorized today, tomorrow, every day of class. If you're going to go into calculus, this one's not going away. Most of the stuff isn't going away, honestly. I really try to be honest with you about what you will see again and what you might not see again. Usually I emphasize what you'll see again, and then you can use process of elimination from there. But difference of squares. So if you have something like x squared minus 9, or x squared minus 25, or x squared minus 36, and it doesn't have to just be x squared. It could be 4x squared, or it could be 4x squared minus 64y squared. You can have variables and numbers in both terms. Whenever you think you've got that kind of setup, you have to factor this as a plus b times a minus b, where a and b are the square roots of the original terms, if you want to be technical. But what most people just say is they're trying to come up with something that when you square it, you get the original terms. So for instance, x squared minus 9 would factor to be x plus 3 times x minus 3. That's weird. No. I got a bad feeling. Um, I think I have had this happen once before. Let's try closing and opening. Let's see if it was working in the other one. It's working in this one at least. So I can always just write somewhere else. Factoring. Oh, hey, let's have one weird thing lead to another. Well, either way. There we go. Okay. Technology, am I right? So something like x squared. I wanted that in red though. Why? I'm just messing this up even worse. I think I fixed it. Fingers crossed. All right, so if you had something like x squared minus 9, the factored form would be x plus 3 times x minus 3, something like that. Because x squared is, it sounds redundant, x squared and 3 squared is 9. That's when there's a minus between them. When there's a plus, you can't factor it using real numbers. Please notice how I just said that. The sum of squares is prime in terms of real numbers. So if you had x squared plus 9, what you would say for now in this course, notice I'm saying for now, is it would be x squared plus 9. You couldn't factor it. You just call it prime. In terms of solving it as a quadratic equation, we have to go another route besides factoring. And that's the thing about these polynomials. If you were to just randomly create or randomly find a polynomial in the wildlife, just scurrying around, there's about a 95 to 98% chance it's not even factorable. Most polynomials are prime. But you might say, well, that doesn't feel right because in my math classes, almost all of them have been factorable. And that's because we are designing them to be factorable. In the real world, when things can be chaotic and disorderly, if you just have random numbers, usually they're not factorable. So this idea of being prime is actually pretty common when you deal with the real world. So if you're trying to solve by factoring, but it's prime, you can't solve by factoring, so you'll need alternative methods, which we'll get into. So sum of squares, for now, we say it's prime. By chapter, 3, we'll learn a way to factor using imaginary numbers, but we won't really use it too much at this level. Then you have the sum of cubes and difference of cubes, and these two pair together. You should really memorize these as a pair because you look at this a squared, b squared. There's a lot more going on the right-hand side versus the difference of squares. And a lot of students will try and memorize these independently. I'll be honest, when I had algebra, I think I saw this formula the first time in Algebra 2. My teacher didn't tell us to memorize them as a pair. They said memorize them one by one, and it was annoying. I didn't like it. But if you really kind of make an observation, half of it's pretty easy to remember because the a squared, b squared pattern is the same in each of these. Whether it's a sum of cubes or a difference of cubes. See, there's no prime going on here, and it has everything to do with the even or oddness of the exponents. Remember, an I comes from a square root of -1. But these are cubes, so trying to solve it feels like a cube root, which it's okay to have negatives of. All right, so it doesn't matter if this one's a plus or minus. It's the cubes where it does. Minus okay, plus no. So a squared, b squared. That's the b pattern, no matter whether it's a plus or minus. Then I've got this nice little mnemonic device, kind of like foiling or PEMDAS. I use what I call SOAP. Yes, your math teacher is telling you how to use SOAP, my classic joke. So SOAP stands for same, opposite, always positive. It tells you the order of these signs. The first sign is the same as the original sign. So if it's originally plus, the first one's a plus. If it's originally a minus, the second one's a minus. By the way, if you're not writing all this down, that scares me, especially if you're weak when you're factoring. The O stands for opposite, so the second sign is opposite of the first sign. So if the first one's plus, the second's minus. If the first one's minus, the second one's plus. And the last one is AP, always positive. So the last one goes together, always positive. No matter what, the third one is always positive. And if you don't trust these formulas, if you want to go through and be meticulous, multiply out the right-hand side. You'll have 6 products to do. You'll see a lot of canceling, and you'll end up with the a cubed plus b cubed or a cubed minus b cubed, whichever it's supposed to be. You have got to have all 3 of these formulas memorized all semester. When you go on to calculus, you're going to need those formulas memorized all semester. If you're going on to pre-calc 2 before calculus, depending on the type of calculus you take, guess what? These formulas will pop up in there every now and then. Even though it's trigonometry, you'll still see it occasionally. You never, ever get to forget these formulas the rest of your life in math. Now, when you stop taking math classes, if you don't have a career involving this stuff, sure, forget it then. So I didn't give any examples of difference of squares here, but I did write one really quickly in red up there. But down here, I did give an example of a sum of cubes. The only difference here would be the signs if I made that a minus 64. So this is the process I go through. Now, if you think differently, if you operate differently, you do your own thing as long as you can get to the answer. But here's the way I do it. X cubed plus 64. This 3 tells me I should be doing the cubes formulas, not the squares formulas. So A would be the x, because if you cube x, you get x cubed. And B would be 4, because if you cube 4, you get 64. Again, it's like taking a cube root of what you see there. So we take the original thing, and all I do is A, B, A squared, AB, B squared. Now, I went ahead and swapped the order of the 4 and the x. So the a times b would be x times 4, but we, of course, want to write 4 times x instead. It's just more proper. But I did not put any signs in between these terms yet, because it didn't matter what this was. If it was plus or minus, this right here, this binomial and trinomial would be exactly the same. The 16 was the 4 squared, by the way. 4 squared is 16. So because that's a plus, though, then we can use SOAP, same, opposite, always positive, to get the signs correct. And again, if you don't like my mnemonic device, you don't have to use it as long as you got a way to get it right. So SOAP, same, says the first one should be a positive, so we make it a plus. Opposite says the second one should be a minus, and the third is always positive no matter what. So if we had x cubed minus 64 instead, that was a minus, it still would have gone x 4, x squared, 4x, and then b squared, the 4 squared is 16. That is exactly the same. But what would be unique is these signs would be different. The first would be the same as the original, so minus. The second would be the opposite of the original, so plus. The third would be always positive. Practice this. If you're rusty with it, or for some reason you've never factored cubics before, which terrifies me, again. And I bring these points up because of this self-enrollment process that we have at TCC now. It's possible that you put yourself in this class without having the necessary prereqs, because they don't tell you, well, no, you didn't take this, so you can't take that. You can just say, hey, put me in pre-calc, doc. Maybe you shouldn't be here. I don't know. I haven't had, hour-long conversations with every single one of y'all. That's what the counselors are supposed to be doing to put you in the right place. So again, I'm not trying to terrify everyone. I'm just trying to make people aware that you could be lacking some of the things that you're not supposed to be lacking in here. In which case, if you want to stay and try and keep up, you've got to fill in the blank, so to speak, and do those extra assignments, go to the internet for extra work, go to tutoring, whatever you have to do. I sent the tutoring. Yes, I did send the tutoring document. Okay, cool. So those are our binomials. Now, there are formulas for some trinomials, things with 3 terms. So I'm going to kind of add something to the side here, that we have some formulas for trinomials. And that's I'm writing the wrong side, swapping my left and right side. It goes a squared plus 2ab plus b squared is equal to a plus b in parentheses squared, and a squared minus 2ab plus b squared is equal to a minus b squared in parentheses. So these are what we call our perfect square trinomials. We will actually use the idea of this for something known as completing the square. But we don't really manually do this factoring hardly ever. Sorry, I got stalled out there in my thought process. The stuff I'm going to show you is what would generally be usable. Anytime you actually have to use this formula, we kind of just pull it out of thin air, as we'll see in examples later. Okay, so factoring trinomials. I'm going to give you two primary methods. The naming convention I have for them are the shortcut method and the AC method. Some people call the AC method grouping because that's one of the things you do in it. Also, I call it the AC method because that's one of the things you do in it. The reason I call this first one the shortcut method is because it's a shortcut of the AC or grouping method. Some of you may have heard of the box method. Some of you may have heard of, I think it's called the push and pull method. I'm not going to be teaching those. Again, if you are fluent in them, use them. I don't care, but I'm not going to teach 50 different ways to factor something. The third primary factoring method that's classically taught is trial and error. I'll describe it. I don't really emphasize it a lot because it's something that you need to do hundreds of times to get really, really good at. Whereas this AC method I'll give you, you really only have to do maybe 10 to get really good at. And it's just because it's a lot less of a guessing game. So I'll explain that when we get there. All right, so shortcut method. List the pairs of numbers that multiply to make C, but add or subtract. Add if it's positive, subtract if it's negative to make B. And when I say it, I mean the constant at the end. So when I say factor something like x squared plus 5x, x squared plus bx plus c, I'm saying something like x squared plus 5x minus 6. These don't have to be all pluses. You can have minus signs wherever. The main idea is that the leading coefficient is 1. There is no number in front of that x squared. I'm not saying that's a 0. I'm saying there's no number in front of the x squared. When there's no number in front of the x squared, you can use a shortcut approach. So you're taking this number along with its sign at the end. This will be a constant. And that's what we're doing in step 1. We're writing all pairs of numbers that multiply to make that. And you're going to try and find a pair that adds or subtracts to make the middle number. We're trying to make this number. We're finding pairs of numbers that multiply to the red thing, but add or subtract to the blue thing. How do you know whether you're adding or subtracting? It's based on the red number's sign, the C's sign. So you'll give them signs based on it to make the B. That's what I was talking about with the blue. So the blue is trying to make the numbers appropriately to that. And then your factored form is always x number with a plus or a minus. I'm not using an actual plus or minus symbol. I'm saying it's one or the other, but I can't type that in Word appropriately. So it's something like x plus 3 times x minus 5. And the numbers are what you chose between steps 1 and 2. So the example I give is and I'm actually going to give a little space to show you how I write this out personally, which again, you don't have to. So for x squared plus 5x minus 6, what I do is we take this number, including its sign, and I'm going to write it to the side. And I draw a little upside down V, and then I'm going to write all the numbers that multiply it to 6. 1 times 6 or 2 times 3. And you can see that explanation below, but I'm just showing you how I do it by hand. So that's step 1. Notice I wrote the sign. Even if this was a plus, if this was a plus 6, I would have written the plus here because we're going to need that to tell us whether we're adding or subtracting in the next instance. But it was a minus, so let's leave it that way. So then we're going to try and make sure that they are, since this is a minus, we're subtracting to try and make the 5, and it's got to be a positive 5. Because 1 and 6 and 2 and 3, it seems like either option could work because 6 minus 1 is 5, but 2 plus 3 is 5. But this sign means that the product has to be negative. They have to multiply to make a negative 6, whatever we choose. So if you choose the 2 and 3, 2 times 3 is 6. If you choose these both positive to make them add to a positive 5, well, positive 2 times positive 3 is positive 6, not negative 6. Remember how I said that you need to be really good at your arithmetic with signs and that your calculator's not going to save you because there's something that you're going to have to just have this implicitly known very well. This is what I'm referring to. Factoring is where your sign math has to be in your brain. You have to be decent at this. Your calculator is not going to save you. It can, but it's going to take you 5 times as long to do it probably, and that's not good. All right, so we're trying to make a positive 5. So we're trying to make a positive 5, but the product has to be negative. If I choose 6 and 1 to make a 5, I'd have to have opposites, positive 6 and negative 1. So that's out. 2 and 3, you know what? I was looking at a plus sign, excuse me. I was looking at something else. I was looking at this when I said that, pardon me. That's what I don't like about this teaching method. All right, this minus says we're supposed to subtract them as I said. If we subtract 6 and 1, we get 5. If we subtract 3 and 2, we get 1. So 1 and 6 is actually our choice, again, because we're supposed to be subtracting the pairs because this was a negative. But then we have to give them signs to make sure they add to a positive 5. So they have to be opposite signs. I'm going to do this wrong at first. If I go negative 6 and positive 1, well, 1 minus 6 is negative 5, not positive 5. So I need to swap those signs. It needs to be a positive 6 and a negative 1. So therefore the answer is x in the first spot of each parentheses, and then a minus 1 and a plus 6. Now check this out. You can go minus 1 and then plus 6, or you can put them in the opposite order. You can put the plus 6 first and the minus 1 last. It doesn't matter. I like to go in the order I see though, so I'll keep it the original way. So again, there's all the typed up explanation you would have seen in your notes already, but this is how it looks by hand. If you're not doing this upside down V stuff, if you're not showing the side work at all, if you are good enough to go straight to the factored form and you get it right 100% of the time, then we're cool. I don't need you to show the work. If you're struggling, if you're getting them right 75% of the time or even worse, then you need to show your work and you need to practice, because this factoring stuff is going to be just a minor step in a much bigger game. So that's our shortcut method, when the leading coefficient is a 1, when there's no number in front of it. Next up we have, I'm just going to hit enter a couple of times so we can see all this, the AC method. Again, please write this stuff down. Don't just look at it and think you've memorized it already. That's probably not the case for most of you. Take good notes. Oh, but Mr. Beckner, you typed this up for us. I can just read it later. If you learn by writing, that's not going to help you. If you're terrible at organization, it's not going to help you. I have a feeling organization is lacking for some of us in these times, having to work in much different conditions. And it's understandable, but we have to do our best. So the AC method is called the AC method because in the first step, you're going to multiply the A and the C, the leading coefficient and the constant. That's what they are known for. That's why it's called the AC method. So the AC method is called that because you multiply A and C. This was one of the shortcuts in the previous method. All we did was just use the C. Now we got to use the A times the C for some reason that you just want to trust me on. I explain why in an Algebra 2 class, but we don't have time for that explanation here. Then you list the pairs of numbers that multiply to make this value, but add or subtract. Same, add if it's positive, subtract if it's negative, make B. This step is literally the same step as what step 1 was in the shortcut method. List the pairs of numbers, multiply, blah, 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 blah. List the pairs of numbers, blah, 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 blah. Exactly the same thing. It's just instead of only using the constant at the end, you have to multiply the leading coefficient and the constant. The reason the shortcut method works in that regard is because the leading coefficient is a 1, so 1 times the constant will always be the constant. So this is the exact same thing we did before. Here's where things change. Instead of, and this is the real shortcut of the shortcut method. The shortcut method says we went straight to the answer. Oh, it's just X is in the first slots and the numbers in the second slots. When that leading coefficient is a 1, you might have numbers that need to go here, like a 2 and a 5, something like that. So we can't just use this approach. So what we have to do is, and again, give them the signs based on combining to B, but you have to split the middle term into 2 terms. You are going to create a 4-term polynomial. You're going to take something that had 3 terms and make it 4. And you might go, well, why on earth would we ever want to do that? That seems completely unreasonable and silly. Why would you take 3 terms and make them 4? Because there's going to be something that as long as you can make it this far, I 100% guarantee that the problem you can finish factoring by doing something known as grouping. What is factor by grouping? Because that technique is specifically for 4-term polynomials, unless you say factor by grouping for 3-term polynomials. See below, we'll see below. So factor by grouping for once you have your 4 terms, which again is needed for the AC method. So this is part of the AC method, but it can also be its own problem. I can give you a 4-term polynomial, and the only way you'll know how to factor at this level is by grouping. So you take the GCF from the first 2 terms, you take the GCF from the last 2 terms, greatest common factor. So we're mentally going to split these things in half. First 2 terms, take out a GCF. Last 2 terms, take out a GCF. Now, with the last 2 terms, you'll also have to take out a sign. You'll have to take out a plus or a minus because, well, it would look wrong otherwise. The reason you don't have to do it for the first part is because there's nothing that's going to be in front of the first GCF, so you don't have to write a plus. I'm going to give you a super hint for that that I do not have typed up there. Good. If the parentheses match, which is what you're hoping for, then the parentheses is a 3rd GCF. I'll show you, well, you can see it right here. This step 3 is exactly what we're talking about right here. So pretend like you don't see this yet. So after you do steps 1 and 2, you'll end up with something that looks like this. So here was your GCF from the first term. Here was your GCF from the second term. So let's ignore all of this stuff for now. We're just looking here where it says so. This 5x minus 1 is part of the first term. This 5x minus 1 is part of the second term. It is a product that is in 2 terms, which means it is a common factor. Product means factor. So that would mean your GCF is that parentheses, 5x minus 1. So whenever you have a GCF, you write it first, then you open another parentheses and you write what's left over. And after you write what's left over, it turns out this is what you get. So here's your GCF of your 5x minus 1. There we go. Then you open up your parentheses. And what goes in here, what I do is I say just use your hands to cover up the GCF in the previous line. So where we have all the blue and the red ink right here. So me covering this with black ink is going to be me covering it with my hand. So this is me covering the 5x minus 1 with my hand. This is me covering the 5x minus 1 with my hand. What do you see left over? You see this x and this minus 3, and that's exactly what goes in the other parentheses, x minus 3. That's the easy way to factor out a binomial GCF. Write it first, just like with any GCF. Open your new parentheses. Mentally cover up the GCFs in the previous line. Whatever you have left over is what goes in the next parentheses. And if you don't trust this, you can FOIL everything out and you should get the original equation. So that's factor by grouping. And then that hint I gave you for step 2. If the third term has a negative, it's 99% likely you need to factor it out. I'm estimating with the 99%, but it's really freaking close to all the time. So that's a super awesome hint for, all right, what sign do I take out for the last 2? Do I take out a plus or a minus? What you can do is what I call the productive struggle, where you just take out a plus, and if the parentheses don't match, go back and take a minus instead, because that'll probably fix it. But the hint will help you skip wasting time and just say, all right, if the middle term's got a negative sign, then that means you need to pop out a negative. And that's 99% effective. You know, plus or minus 1%, something like that. Maybe 98, maybe 99.5, I don't know. You get the idea. In Math 161, it'll work all the time. That's what I'm trying to say. In the real world, it's going to fail once or twice. All right, so once again, This factor by grouping, this is its own process. So what I'm going to do really quickly is one example of just factor by grouping, not the AC method. This is my favorite example to do, x squared plus 2x minus 4x minus 8. So this is 4 terms, 1, 2, 3, 4 terms. There are more factoring methods for 4-term polynomials. We don't need them in this class. You won't need them in this class, I promise. 1, 2, 3, 4. Is that right? Yeah, that's right. And you might say, oh, we'll combine the middle terms. No, don't do that. I've set this up for a reason. This might be x cubed plus 2x squared minus 4x minus 8. That would be setting it up so you didn't have like terms, but I want to go ahead to this point. All right, so for the first pair, the GCF would be x. Between x squared and 2x, the GCF is an x. So when I take out that x squared divided by x is x, and positive 2x divided by x is a plus 2. Now this is our goal for the next parentheses. If we can't make the next parentheses that in some way, shape, or form, it's not factorable for us. But I can guarantee you any problem you see, it will happen if that was the point of the problem. All right, now for the second one, you have to take out a sign, either a plus or a minus. I'm going to do this wrong at first, and I'd say red for wrong, but I'm going to keep it red once it's right. So this is wrong for now. I'm going to try taking out a plus. And then between 4x and 8, the GCF would be 4. When I do that, I have negative 4x. Watch your signs. This is negative 4x divided by positive 4, which is negative x. I was trying to write a 4 there, and that's not what it is. It's negative x. And then negative 8 divided by positive 4 is a negative 2. This and this are not the same, but you might notice they're almost the same. They have the same x and 2, but different signs. So that's what I call the productive struggle, where instead of taking out a positive 4, let's try and take out a negative 4 instead. So the red's not wrong anymore. This will be correct. Now divide out that negative. That negative is part of the GCF. So negative 4x divided by negative 4 is positive x. Negative 8 divided by negative 4 is positive 2. Now they match, so our third GCF is x plus 2. So what we do is we write that common GCF first. We then open up a new parentheses, and what's going to go in this is everything that wasn't the GCF originally. So cover up with your hands or your eyes or whatever those GCF parentheses. What do you see left over? An x and a minus 4. So that's what goes here. Now I don't want to leave the scribbling there, so I'm going to uncover my hands now. The x and the minus 4. Again, that was the x and the minus 4. So color-coded. Now, will you see a lot of factoring with 4-term polynomials in this course just out of the gate? No, it's pretty rare, maybe 5 to 10 throughout the semester in total. Let's say 10. But if you're going to go with what I call this AC method, this is part of the AC method, so you're going to have it down. Now, maybe you don't like this AC method. Maybe you go with the box method or the push and pull method or trial and error, which I specifically point out here that is an alternate method. I don't care how you factor, as long as you can factor. So if you love trial and error, use trial and error. I'll even be honest, when I'm factoring on my own, when I'm not teaching, I do trial and error 99% of the time. It's very rare that I do the AC method. But as a teacher, as a quicker tool, the AC method is easier to just pick up, because with trial and error, its namesake is exact. You might have 20 different options for a solution for the factored form, and you might get it right on the 20th try. And that's frustrating, because the person next to you might get it right on the first try and they just have better luck. And we don't like luck coming into this too much, but hey, life's always about luck just a little bit. The AC method, there's no luck. If it takes you 4 minutes to do one problem, it's going to take you 4 minutes to do pretty much any problem. Whereas trial and error, you might do one problem in 30 seconds and then the next one in 15 minutes. Now, if you're someone who's done trial and error 300 times, you're probably pretty efficient at it and don't really need the AC method. However, you might come across a problem where the trial and error method is just a nightmare because there's 200 options, and you go, well, maybe I should try the AC method instead. It's good to have options. So don't be stubborn and set in your ways. Maybe try learning the new method as well if you've never seen it before. All right, so multiply the A and the C. List the pairs to make the B. Adding and subtracting is appropriate. Then you'll give those numbers appropriate signs. It's all really part of the same step. but then you split the middle term. So you might take something that's originally said a plus 5x and turn it into 6x minus 1x. You'll now have a 4-term polynomial that you factor by grouping. So let's try out this example, 5x squared minus 16x plus 3. I am taking way too much time to do this, unfortunately. That's okay. That's okay. So I'm going to do the AC method. We take the 5 times the 3. I even like to spell it out. So AC equals 5 times 3. If there was a negative 5 and a negative 3, I'd include their signs. 5 times 3 is positive 15. Remember, this sign is important because it's going to be telling you whether to add or subtract the pairs. So try and write it. List the pairs, so 1 times 15 or 3 times 5. Now find the pair that adds to make the middle number negative 16. Well, 1 plus 15 is 16, 3 plus 5 is 8, so we need to choose the 1 and the 15. But we also need to give them signs. Give these two numbers signs based on adding or subtracting to the b. So we need to make them add to a negative 16. If we make them both positive, 1 plus 15 is 16. But it's positive 16, so that's not going to work. They're both going to have to be negative. Now you might say, why can't they be opposite signs? Because then the product would be negative and the product has to be positive. This sign is the sign of the product. So again, there's a lot of sign math going on all at once that you have got to be masters of. Now this does not say the answer is x minus 1 times x minus 15. That's wrong. This is where we're splitting the middle term. So we go equals 5x squared. You don't have to write the 1, but I will for detail. Minus 1x. Now whatever this had is what goes with the 1 and the 15. And then minus 15x, then the plus 3. See this minus 16x, I have split into minus 1x and minus 15x. If you recombine them, you'll get the original problem, but do not do that because then you're going in circle, you're chasing your tail. Now we factor by grouping. We take a GCF out of the first pair. Between 5x squared and 1x, you can only take an x out. 5x squared divided by x is 5x. Negative 1x divided by x is a negative 1, not a blank, not a 0. I gave you that hint previously that said whatever the middle sign is, the sign of the third number, that's generally what you need for your GCF. So because that's a negative, I'm going to take a negative GCF out. Between 15x and 3, the biggest thing that goes into that is 3. Open parentheses. Watch your signs. If you don't pay attention, you might make a mistake. Negative 15x divided by negative 3 is positive 5x. That's good so far. Positive 3 divided by negative 3 is negative 1. Our parentheses match, which means it's a third GCF. So we pop out the 5x minus 1. We then open another parentheses, and inside of this goes everything that wasn't the GCF above. So cover up those parentheses with your hands. This is me covering up my parentheses. All I see left over is x minus 3. So that's what goes in the next parentheses, x minus 3. We can see the same thing typed below. I will unscribble some stuff now. Again, those were in your type notes already. Same answer, 5x minus 1, x minus 3. The order of the parentheses, once again, don't matter. You could write it like this, x minus 3 times 5x minus 1. Same answer, nobody cares ever. It's perfectly fine. (5x squared minus 16x plus 3). Okay, so let me show you what trial and error would look like for this problem, which is actually a very short trial and error. Let me not do it that way. Let me just do, I'm gonna do this. Nope, not that. It's fine. I'm not gonna be saving that document anyways. So trial and error, T and E for trial and error. No, what are you doing to me? Draw. T and E. And this was for 5x squared minus 16x plus 3. Right, 5x squared. Yeah, minus 16x plus 3. So trial and error looks a little different. You're still going to be splitting up numbers into pairs of multiples, but you do it for the A and the C instead. So for the A, that's splitting up 5, which is 5 times 1. For the C, that's splitting up 3, which is 1 times 3. And then you're just going to use these numbers in pairs of parentheses. The 5 and the 1 would go with the x in the first slot. The 1 and the 3 would go just to the numbers in the second slot. But you have to swap things around. So it could be 5x times 1x. Let me do these in black, actually. 5, 1. And then the other one, we'll put the 1 and the 3 here. So the 1 could go there and the 3 could go there. Or it could be 5x, 1x, the 1 and the 3 could be swapped. Now, if you're swapping the latter pair, you don't have to swap the former pair, so I don't have to try swapping the 5 and the 1 because that would just replicate one of the other two scenarios. Now, if both of these scenarios fail, then maybe you have another option. So if this number was, say, 15, you could go 1 and 15 or 3 and 5. So maybe the 1 and the 15 fail in that order. Maybe they fail 15 and then 1. So then you got to try the 3 and the 5 and the 5 and the 3. But this is an easy one because there's only one option in for each of these. So then you just got to give pluses and minuses to make all the arithmetic work out. So the product has to be positive, which means these have to both be the same sign. If this was a negative, they'd have to be opposite. And again, that's just under the idea of multiplying two positives, two negatives, or opposites, and how they give us signs. But we got to make sure that the sum comes out to a negative. So if they have to be the same sign, but the sum is negative, that means they'd have to both be negatives. And then you can just FOIL this out to check. So you get 5x times 1x is 5x squared. 5x times negative 3 is negative 15x. Negative 1 times negative, so positive 1 is a negative 1x. Negative 1 times negative 3 is positive 3. When you combine, you get 5x squared minus 16x plus 3. And we actually got the answer right on the first try. So that trial and error was awesome because we got it right on the first try. Maybe another student did this one first. Maybe they tried the second one first and they got 5x squared, then times a minus 5x, then minus 3x, then a plus 3, which would have given us 5x squared minus 8x plus 3, which is wrong. So again, someone could have tried the second one first, got it wrong, and then went and did it the first way and got it right. There was only 2 trials to do here. There are plenty of trinomials that have 20 or 30 or 40 or 50 or 60 different trials though. Trial and error sucks for them. I would say on average for this course, it's usually in the ballpark of 8 to 16 options. But even that's pretty bad. But if you've done this a lot, you might have cases that are very obvious to throw out and you don't have to worry. All right, so that's our extended factoring discussion. So with that in mind, we are now masters of factoring. We can go on to actually solving our quadratic equations. So there's 3 primary methods that we will discuss. Solve by factoring, quadratic formula, and completing the square. For people who are awesome at factoring, they love the first one, but again, in the real world, it fails 98% of the time. In a math class, it works 98% of the time, probably, and for us, more like 50 or 60. Quadratic formula is typically people's second favorite. That's that big formula that you all should have seen before, negative b plus or minus, blah, 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 blah. We'll write it down sooner than later. Completing the square, most people's least favorite. I'm not saying everyone's, I said most people's. It's a lot more methodical. The steps feel very much like, why the heck am I doing this? But here's the fun thing. You know where the quadratic formula came from? It wasn't just created out of thin air. Someone took completing the square. They did it with the general ax squared plus bx plus c. They completed the square on it, and that's how the quadratic formula was derived. So the quadratic formula comes from completing the square. So you have to at least appreciate completing the square, because without it, there would be no quadratic formula. It wouldn't exist. I wouldn't say it wouldn't exist. It just would have had to have been developed in another way, and I'm sure somebody could have done that. All right, so, and this is for ax squared plus bx plus c is equal to 0. This is our standard trinomial that's quadratic. It's quadratic because the biggest exponent's a 2. Now the leading coefficient could be a 1. It could be any other number in the world. The middle term could be missing. The constant could be missing. You don't have to have all 3 terms always. That's why we have binomials. But you have to have that leading term. So how do we go through this? To solve by factoring. First step, move all terms to one side so that the other side is 0. Second step, factor. Now that word, that one word, those 6 letters, that is a giant loaded statement. Because factoring could mean one of the formulas, sum of squares, difference of cubes. I said sum of squares, I'm going to say difference of squares. Difference of squares, sum of cubes, or difference of cubes. Or it could be the shortcut method, or it could be the AC method, or trial and error if that's what you prefer. Then, after you factor, you set each factor equal to 0. Solve independently. Independently. This is what we call the 0 product rule. Think about this. If you have 2 numbers, I don't tell you what the numbers are, so I'm going to call them A and B. If you have 2 numbers, but I tell you they multiply to 0, you can't really tell me anything about the numbers except one of them has to be 0. That's all you can tell me. So 2 numbers that multiply to 0. They can't be 5 and -9 because that would multiply to 0. I could tell you that the first number is 5 and I ask you what's the second number? Well, it has to be 0. Or I could tell you that the second number is 9 and what's the first number? It has to be 0 in order for them to multiply to 0. Well, when the 2 things you're multiplying by have variables, they can be 0 at different times. So that's why we get to set them equal to 0 completely independently. This is one of the simplest and yet strongest rules we get in math because it enables us to break down something that's of a higher order to a lower order. And that is amazing in math. We want that whenever we can, to break something down from a cube to a square, from a square to a linear term. So after you do that, well, you're actually done. I didn't mean to have a step 4, it's just me hitting enter in Word. 3 steps. You could say that the 4th step is solve them independently. And they are generally going to be very easy equations to solve independently as long as you're factoring correctly. Example 1. Solve. Come on, what are you doing to me? There we go. A. And we're going to start out with x squared plus 8x is equal to -15. Now, these don't have to start with just 3 terms or just 2 terms. They can start out with things that need to be multiplied and like terms to be combined, all sorts of things on both sides. They don't always have to be all on one side. They don't always have to be in a nice, pretty easy form. So please note that the homework problems can stretch you a little thinner. But I want to focus on the main tactics here. So you need everything on one side. In order to factor, you need everything on one side. So what you have to do here, you could move the x squared and the 8x to the right, but I'm going to give you a hint. You really want that leading term positive. Having a leading term positive makes factoring significantly easier. So while sure you can move those 2 left terms to the right side, it is much easier to move the 15 to the left side, giving us x squared plus 8x plus 15 equals 0. And it's at this point that we factor. So the leading coefficient is a 1. There's 3 terms. So I'm going to do what I call the shortcut method. I can just go ahead to saying this. The factored form is going to be x and then a number and then x and then a number. To figure out what number goes in there, I go to the side. I'm going to take that 15, this plus 15, and I'm going to go to the side and split it up. So Here's my side work. My positive 15 could be 1 times 15 or 3 times 5. We need these pairs to add to make a positive 8. That's our goal. Well, if we're adding them, 1 plus 15 is 16, so that's out. 3 plus 5 is 8. That's in. We got to make sure it adds to a positive 8, though, so I can't make them a negative and a negative because that would add to a negative 8. I can't make them opposite in signs because the product wouldn't work anymore. They both have to be positive. So it goes x plus 3 times x plus 5. If you don't trust it, FOIL it, it works. So now we're going to step 3, set each factor equal to 0. So this is what I meant by something times something set equal to 0. But because these somethings have variables, they can be 0 in their own instance. So we take the x plus 3 and we set it equal to 0. That's a weird looking 3, isn't it? Come on, there we go. Then, completely independently, we take the x plus 5 equal to 0. I can't do that. I can't just set x squared plus 8x equal to 0, negative 15 equal to 0. That fails miserably. Then, simple algebra, subtract 3 on both sides for the first one, subtract 5 on both sides for the second one, and then you get x equals negative 3, and x is equal to negative 5. So this is pretty common, multiple solutions. It's not just one solution, it's two. You could get 3 or 4 or 5 solutions. You can get repeated solutions. We will see all of these cases, ultimately. All right, let's do another. And by the way, if you want to check them, you can. You're not forced to check them, but they will work if you put one of these numbers in at a time. The left side will match the right side. All right, everything's already on one side for this one, so step 1's taken care of. Again, don't always expect that in your homework or on a test question. I'm just trying to get down to brass tacks, especially considering our shortened time. The leading coefficient is not a 1 this time, it's a 2. And there's 3 terms. So we're going to have to either go with the, if you're using my methods, the AC method or trial and error. Trial and error has got 2 options for splitting up the 4. So it's not as great as the one I showed you previously, but it's still only 4 options in total, so that's not awful. But again, I want to emphasize the AC method because I feel like more people haven't seen it. So to the side, I can't say I know anything about the factored form. I can't do that. I've got to take the A times the C, which is the 2 times the negative 4, which is negative 8. Then you're splitting that up, 1 times 8 or 2 times 4. Same idea. You're trying to find a pair of numbers that adds or subtracts to make the middle number, specifically subtracts because that's a negative. And we're trying to make a positive 7 out of these. 8 minus 1 is 7, 4 minus 2 is 2. So I think it's clear that we need to choose the 8 and the 1. But we got to make sure that difference is a positive 7. If you go positive 1 and negative 8, that would make a negative 7. So make sure that you get your sign orientation correct, because that one little error would screw everything else up. Now it's not x minus 1, x plus 8. What I'm doing is wrong, but this is what I see students do. X minus 1, x plus 8 equals 0. Then they'll add 1, subtract 8, and they'll say the solutions are 1 and negative 8, and it's wrong. And my math lab won't give them any partial credit, and it's because you factored wrong. So let's do it right. We're supposed to split this middle term. Let's just split that middle term up. So we get, leave the first one alone, 2x squared. Leave the last one alone, minus 4, and the equals 0. That plus 7x is going to become a minus 1x plus 8x. Now what's cool is, I know one of you probably wants to ask this, but just hasn't. You can swap the order of the minus 1 and the plus 8. I can write plus 8x and then minus 1x. You'll get the same answer in the end. Then we factor by grouping, 1, 2, 3, 4. So we factor by grouping. That's where we're visually splitting this in half, and I see some people actually just leave that there, but I'm not gonna. GCF from the first pair. So GCF from the first pair would be x. Take out an x, because you can't, there's no number that goes into 1 and 2 besides 1. 2x squared divided by x is 2x. Minus 1x divided by x is a minus 1. Even if that one wasn't written there, it's implied, but you would have to write it here. Now this middle sign is a plus, so my super top secret hint is that will be a plus and that will work. The GCF between 8x and 4 is 4. Open your parentheses. That was not enough room. 8x divided by 4, positive, positive, gives us 2x. That's a good sign. Negative 4 divided by positive 4 is a negative 1, also a good sign. Don't forget your equals 0. Alrighty. Now, this 2x minus 1 is the same thing as 2x minus 1. They're the same, so you've got a third GCF of 2x minus 1 in parentheses. So we write that first. That's what you do with GCFs. You write them first. Then you open a new parentheses. And again, we're just, the way the division works is you can just mentally cover this up. Use your hands to cover it up. What do you see left over? X plus 4. That's what goes next. If you FOILed that out, you would get the original problem. Then we're going to split this up using the zero product rule. So we go, oh, why do I have equals on the left sides? I don't know why I was doing that. Those should not be there. I'm sorry about that. This is terrible notation. Because the equals is in between the sides. You don't want to have an equals here. That was a big no-no. I apologize for that. Please correct that. Please erase those. So we have 2x minus 1 equals 0, and x plus 4 independent to it equal to 0. You're going to add 1 and divide by 2 on both sides of the first one. You're going to subtract 4 on both sides of the second one. You get 2x equals 1, x equals negative 4. That one's done. You have to divide by 2 on the first one, though, to finish it up to get your x equal to a half. So 2 solutions. One of them is a fraction, but that wasn't a problem throughout the problem. That wasn't an issue throughout the problem. That is the same. You have got to be able to factor all these different types of problems. These numbers are pretty simple. They can be a little bigger in the homework. In terms of testing, they're usually in the ballpark of the homework, but not the worst possible cases. I'm not going to give you 3-digit numbers to factor, for instance, unless it's just, 121 and in a difference of squares. Sorry, I'm looking for something that I seem to be missing. Okay, cool, we're good. There it is, found it. I flipped the wrong piece of paper. So I'm not going to do a whole bunch of these because the main point of these problems is factoring a skill that, once again, you're supposed to have and just be kind of shaking off some rust, not completely learning from the ground up, I hope. But if you are, understand you've got a lot of practice that you will need to do because this will be going on for all semester. All right. So before, and I know that I list them in this order mainly because these are the 2 that people like, and most people don't like the completing the square, so I have it listed as third. But we're actually going to do completing the square before we do the formula, so we at least appreciate the formula a little more. But before we complete the square, we've got to introduce a concept. This concept known as the square root property. I need you to highlight this. I need you to circle it in red and blue ink. I need you to never forget this. And 20 of y'all have already forgot it. I don't even know if there's 20 people looking at the class right now. How many we got? 18. So out of 18, 17 have already forgot it. And I'm not trying to be mean. This is just how it works. If you have any number squared, sorry, if you have not any number, anything squared and set equal to a number, then that means anything equal to the plus or minus square root of the number. Now this plus or minus is the actual literal plus or minus symbol, and we're going to see this for quite a while, not just in the square root property, but in completing the square, in the quadratic formula. This is a very common symbol that we'll see over and over and over. What I'm saying here is, if you have anything squared equal to a number, this is what you will do. You take the plus or minus square root of both sides. But the plus or minus only on the number side. Whatever we do to one side, we do to the other. We're essentially taking the square root, but there's a problem, and this is going to be explained in the first example as we try and do it without the square root property. So you take the plus or minus square root, but you only put the square root on the left side, you put a plus or minus square root on the side with the number. Here's why. Square roots and squares cancel. Why is it when we have x plus 3 equals a number, we subtract 3? Because it cancels. Why is it when we have 5 times x, we divide? Because it cancels. The idea of solving equations is generally rooted, pun intended, around something canceling to make the x a little closer to being by itself. So square roots and squares cancel each other. Cube roots and cubes cancel each other. Fourth roots and fourths cancel each other. So like adding and subtracting cancel each other, multiplying and dividing cancel each other, square roots and squares cancel each other. So when you see something squared equal to a number, you can say, oh, well, I just want to take the square root. But this right here is extremely important, as we will see in a minute. This is the thing that the most wonderful students will constantly forget all semester long, and it will constantly be an issue if they're forgetting that. There are times when that plus or minus isn't necessary, generally when we're talking about applications. But for now, oh, it's going to be necessary. So this is the square root property. When you have something squared, and I'm being general with this, I'm not saying just an x squared or just a y squared, I'm saying anything squared. It can be a parentheses with 10 pounds of trash inside of the parentheses, and then it's squared and just equal to a number. There's nothing else on that side with the trash. You could apply this principle to get rid of that squared. All right. Example 2, solve. Okay, we're going to do x squared equals 16. Now, before I actually go and do this correctly, I'm going to do this incorrectly. And again, more than half of students want to do it this way. They see x squared equals 16, their brain goes, x is 4, because 4 squared is 16. So many students would just go straight to saying the answer is 4 because it seems very clear. Well, obviously 4 is the answer because if you square 4, you get 16. 4 times 4 is 16. I'm done. I got the answer 4. It's wrong in the homework. It's wrong in the test. And you might go, well, I got half the answer right because it says it's 4 and something else. Why can't I get partial credit? Because you didn't actually understand the principle of the problem. So it's not just taking a square root of both sides. It's taking a plus or minus square root of both sides. Plus or minus only goes on the number side. So the square root of our x squared, which I almost didn't write. I was catching up though. Square roots and squares cancel. So the left side is x. That's what you want to see. That's the goal. The square root of 16 is 4. So x is equal to plus or minus 4 in reality. So that student that goes, oh, the answer's 4. Yes, an answer is 4. It is one of the answers, but -4 is also an answer, and nobody said you couldn't use negative numbers. Now, if this was an application and we're talking about lengths of the side of a geometrical shape, sure, you can't have negative lengths, so you toss the negative out in that instance. But I don't see anything that says this is geometry. And again, this is a major problem. My calculus students forget it as well, and I have to remind them of how important this is. And they have their reasons for forgetting it, because in trigonometry, you basically drop this for a while for, again, geometric reasons. So maybe it's just a lack of habit. You don't use it, you lose it. So maybe you don't trust this. Why does -4 actually work? Well, -4, when you square it, is positive 16, because when you square a negative, you get a positive. This leads to what is known as a loss of sign generality. If you just take the square root of both sides, if you just do it this way, because of the x being squared, you don't know if that number originally was positive or negative, because it could have been either, because when you square it, you're going to get 16 no matter what. So you can't tell what the original sign of x is. So because of this loss of sign generality, we have to inject the plus or minus and say, I have no way of knowing whether it was positive or negative, so both are possible. Maybe we throw it out for geometric reasons. Usually not, though. Here's an alternative way that this could have been solved, using what we did in the last pair of examples. Instead of using the square root property, you could move the 16 over to the x squared side. You can solve this by factoring. You get x squared minus 16 is equal to 0. This is a difference of squares, where your a is x and your b is 4, so you go x plus 4 times x minus 4 equals 0. You set each of these equal to 0 independently. Subtract 4, add 4, you get x equals -4 and x equals positive 4. The same two solutions. They're just not written with a single number and a plus or minus symbol, but they're still correct. So if you can solve it one way by factoring and get two solutions, that means that there is two solutions, and you can't just say 4 is a solution. Now you might be thinking, all right, well, I don't need this plus or minus jazz. I'm just going to always solve by factoring. No, you're not, because guess what? That number does not always have to be a perfect square root. Spoiler alerts. X squared equals -4. I'm pulling out the red for a minute. I'm not going to say this is wrong, but this is going to be a dead end. I will erase all of this after I write it up, but if you add 4 to both sides, if you add 4, you'll get x squared plus 4 equals 0. And guess what? Because that's a plus, this is a sum of squares, which means it's prime. You can't factor it. So you'd say no solution, question mark? Absolutely not. What it means is the solutions are imaginary. I've kind of spoiled that factoring a sum of squares leads to imaginary factored forms, which again, imaginary numbers are really things. They're not fake. They're not fake news. We'll talk about what it means to be imaginary later. So that's a dead end. Now, if this is 16, what if this was a 17? So if you had a -17 over here, that's not a perfect square, so dead end. So the factoring version only works if that number is a -1, a -4, a -9, a -16, a -25, any number that is a perfect square. So instead of dead ending, because we can't factor, we have to use this alternative method. We take our plus or minus square root of both sides. But the plus or minus only goes on one of those sides. We do this because square roots and squares cancel. X squared, square root of x squared is just x. If you had the square root of x and then squared, it would be the same thing. If you saw this, if you saw the square root and then the 2 on the outside of that, that is still an x. They cancel the same way. As long as there's no pluses or minuses inside, parentheses can fix that, but we'll get to that later. And then equals. The square root of -4, don't you dare say that's not a real number or undefined. Square root of -4 is 2i, because square root of 4 is 2, square root of negative is an I. So that's 2i, but your plus or minus is still there. Two solutions. Pretty common. How are we on time? A couple minutes. I think we have just enough time to do this last one. This will be the most interesting of the three. This will really test out that anything squared idea. 2x plus 3 in parentheses squared minus 6 equals 2. So this is not just something squared equal to a number. You have to clean this up. You have to make it look like the first two. Now you might say, well, I can't do that because of this parentheses. It doesn't matter. The fact that it's just something being squared, this is what I meant by the anything. Just isolate that part. Move the 6. Now you might think, oh, I need to write that times itself and FOIL it, combine the -6, move the 2 over and factor. You could try that, but spoilers, this problem is prime, so you're going to waste your time. This is a much easier and shorter way to do things. Add 6 to both sides. Just isolate the anything being squared. So we get 2x plus 3 in parentheses squared equal to 8. This is where we can take that plus or minus square root. You can't do it if it's something like x squared plus 5x equals 7. You can't just take a square root like that. You can't do that. It has to be just something squared equal to something else, just a number in particular. All right, so we take our plus or minus square root, not just a square root, plus or minus square root. Leave the parentheses, 2x plus 3 squared equals plus or minus square root 8. We do this because the left-hand side simplifies insanely. Square roots and squares cancel, so the red and the black exponent of 2 all cancel. You just get the inside, 2x plus 3 equals. Now that right side, we don't know the square root of 8, but we can simplify it. We can say that 8 is 2 times 4. I'll put the 4 first because that's the number I know the square root of. It doesn't have to be that way. The square root of 4 is 2. So this is 2x plus 3 equals, now be very careful. First of all, notice I'm leaving a little space in front of the plus or minus. That's a good habit to have. If you don't, you might make a mistake, but this is just good habit with the space here. The square root of this 4 is 2. But the plus or minus has to be in front of that 2. So leave this space, draw, thank you, plus or minus 2, and then square root of 2. So this black 2 is still inside because we don't know its square root, but we know the square root of 4, it's 2, so it's out there. It's not in front of the plus or minus, it has to be after to make sure it's a product. Why is that spacing there? Because now we have to solve for x. Before, this was already just an x equals and we were done. That's not the case here. We've got to solve for x by first moving the 3, subtract it. Now you might think put it over here on the far end, but that's why we left this space. It is critical to have this here so that you don't think the plus or minus is part of it. So we get 2x equals -3 plus or minus 2 square root of 2. Last step, we divide everything by 2. You can do this as a split division on the right or all at once. I personally prefer all at once, but you be my guest and do it the other way if you want. Now, the 2x's on the left cancel. The 2 and the 2 in front of the x cancel, so it's just x equals. The right side, you think these 2's cancel, but they can't, because I did not mean to scratch that, because there's no factor of 2 here. So this is non-reducible in this form. It's -3 plus or minus 2 square root of 2 all over 2. This is the answer. It's not pretty, but this is a pretty common format for an answer with these. You get these ugly answers when they're not factorable. So alternate version of this answer, if you split it, you'd get -3 over 2 plus or minus 2 square root of 2 over 2. Then these 2's you can cancel, giving us -3 over 2 plus or minus radical 2. That's fine. It's not necessarily better. My math lab would take either, thankfully, so you're set. All right, that is perfect timing. We have not finished this section, as I pretty much guaranteed we wouldn't. We still have lots of things to do. So we will introduce the idea of completing the square next class. I'll give you the instructions. We'll do several examples. It's a long list of instructions, so be prepared for that. I'm probably going to go ahead and type it up so I'm not wasting a bunch of our time together for that. But yeah, so we'll continue 1.5.
All right, so like we said, we'll continue 1.5 next time. Remember, the due date will be a week from next class. So the one that you see in my math lab currently, just please ignore, that will change. All right. So besides that, have a good day. Keep up with the homework. Do that prereq assignment if you haven't already. We'll pick up with 1.5 next time on Thursday, as long as it doesn't snow again. Ha ha ha. All right. Take care, everybody.